As of now, we only spoken about fluids in which there is no viscosity, but real fluids have a certain amount of internal friction, internal resistance, known as viscosity. So let's suppose we have the following fluid, we have the following liquid that is traveling along the following horizontal direction. Now, how exactly do liquids move? Well, liquid moves, or particles within liquids move along pathways called streamlines. And the streamlines are stacked, are layered on top of one another as shown. So here we have one streamline, a second streamline, a third and a fourth streamline, and the streamlines along which our liquid particles travel are stacked on top of one another. And the viscosity within these liquids arises from electrical forces between adjacent molecules, which come from the attraction of electrons and protons of adjacent molecules. Now, in gases, the case is slightly different. In gases, viscosity comes from the collisions between molecules. Now, let's discuss something known as the coefficient of viscosity, which is given by a Greek letter eta. Now, where exactly does the coefficient of viscosity come from, and how can we define this coefficient of viscosity? In other words, the higher the coefficient of viscosity, the more viscosity, the more internal friction we have in our fluid. But how exactly do we define this coefficient of viscosity? Well, we define it in the following manner. Let's suppose we have a solid stationary plate on one side and a moving plate on the other side, and between these two plates we have some sort of liquid. Now, the liquid directly in contact with the plate is held together by adhesive forces between the molecules found in the liquid and the molecules found in that solid. So that means that the layer of liquid close to the moving plate moves with the same velocity as that moving plate, and the liquid that is in contact with the stationary plate is also stationary, just like our stationary plate. So we see that the velocity of the liquid between these two plates ranges from a value of E equals 0 to a value of V. Now, we define the ratio of this velocity V with the distance separating our two plates as the velocity gradient. So velocity gradient is simply velocity of this moving plate as well as the liquid that is in contact with the moving plate divided by the distance separating our two plates. Now, in order to move this plate along the surface of the liquid, that requires a force. So, to move the plate with cross-sectional area A over a certain fluid with some viscosity requires a force. And the relationship between the coefficient of viscosity, the velocity gradient, and the cross-sectional area of the plate we're moving, and the force is given by this equation. So force is equal to the coefficient of viscosity multiplied by the cross-sectional area multiplied by the velocity gradient. Now, if we solve for the coefficient of viscosity, we get the following result. So we see that the viscosity, or the coefficient of viscosity, has the unit pascals multiplied by seconds. So from this equation, which is derived experimentally, we see that the greater the viscosity of the object, the higher the force required to move the plate over that fluid with a certain cross-sectional area of A. And we also see from this force, from this equation A, that the higher the distance separating our two plates, the stationary plate and the moving plate, the lower the force. So the higher this quantity, the lower the force is. The higher this quantity and the higher that this quantity is, the higher our force is. So this once again is defined as the coefficient of viscosity. the more internal friction we have within our object, the higher our coefficient of viscosity is, and the higher the required forces to push our moving plate across our fluid.